Okay, now so let's start. Okay, so remember from last time, we studied the integral curves of. Okay, so remember from last time. Yes. Yeah. Ahora sí, ya lo leo. So we studied integral curves of a smooth vector field. And for that, I mean, to get the idea, it is important to have it only on Rn. We did it on a manifold, so this is the definition that we saw the last time. So I have a vector field on a manifold M, and then we define what is an integral curve. So it is a smooth function defined on some open set on the reals. So this is some open set on the reals. It's a smooth function. We have an initial condition that will be the appropriate way from differential equations, or a normalization condition. So we will require that at time 0, the function equals p. So this will be an integral curve through p. This is just the normalization condition. But what is important about this curve is that if I take the derivative, I will get precisely the vector field at that point. So that's the crucial important thing about an integral curve related to a vector field. So that's what we saw last time before the break. We even covered a few examples. And so I just copy here the definition that we saw last time, but we also showed the existence of an integral curve because it was just a differential equation. We have to solve this ordinary differential equation subject to this initial condition. Okay, and so precisely that result from ordinary differential equations is going to give you the uniqueness, right? Once that you have an initial condition, there's a unique solution. So for a differential equation, you have a whole family of solutions, but once that you fix the initial conditions, you only have one. Okay, so, and this is what I would like to stress in terms of this function. So if I already know that I have that function, this is an interval that contains this is A, this is B. By the first condition, the interval A comma B contains the 0 because of this. Okay, so assume that you have that function. That function has its stance. It doesn't have to be unique in the sense that maybe I can take a smaller domain, something like this. A prime and B prime. That's also going to be a function it's just the restriction. It will satisfy this and this, but as functions, they are different because the domain are distinct. So this is just what I wanted to clarify in terms of uniqueness. And also, it will be important in some other aspect that we will see. So remember, this is one of the examples that we saw last time. And do you remember what is the integral curve here? Do you remember? So we need to take a point. Let's take the point 1, 1. What is the integral curve through 1, 1? There are two strategies that you can take to answer this. One of them, remember what we did last time, and the other one, because this is an easy example and a straightforward vector field, you can also work it out in your mind. What will be an integral curve? So we are doing all of this in Rn so that we can actually work it out. And this is something that I was expecting from you guys. So I want a function like this. This is the first entry and the second entry. I would like to find those two functions. And first, I have the conditions. At 0, it has to be 1, 1. And the second one is the system of differential equations. So the vector field, this is just by definition. I'm going to write it like this if you want, right? But I want this to be the derivative, right? So this has to be with respect to t, comma, t. So
example,
here,
it would be like t plus 1, 1.
right, exactly. So the solution is going to be t plus 1, 1, right? Because here you get this system of ordinary differential equations. So this equality gives me this, right? On the vector field x, we don't have the dy. That's why c dot equals 0. And so from this, sorry, you get this is t plus some constant, right? And c2, oof, let me not use c here. let me use A1, a constant. And C2 is just a constant. But now when you plug in the initial conditions, we get exactly what Salvador was saying. This is t plus 1, comma 1. Okay, so that's the integral curve of the vector field ddx at the point 1, comma 1. And something that it is very important is what is the domain. Remember that we discussed that last time. We have to take into account two aspects. First is whatever the system of ODEs tells you. That will give you a parameter for the t to vary between some interval. And also you need to consider the geometry to see if there are no limitations on the parameter t. In this case, it happens that t can be any real number. So a comma b happens to be the whole reals. Okay, so that's the review. So again, I would like to stress the integral curve is just the solutions of a system of ordinary differential equations subject to an initial condition. Now, as I said it here, the function can be different if we take a smaller interval. But if we look, if we have here m, p, if we look at the image of the function, it is this. This is the vector field. If we look at the image of the function, is a curve on M. So that curve can only be, if we change the domain, if we make it smaller, it will be a subset of that curve, right? So the image is just a curve. If we change the domain of the function, it will be a smaller one. And I wanted to talk about this because there's the concept that sometimes it's convenient of a maximal integral curve. And that's when the domain of the curve is the largest that you can take. So it's going to be an integral curve. I have it like this. Remember A and B. Such that if I take another curve, this is a subset of this. So that's what we mean by maximal integral curve. If you look at the image, it describes the biggest curve that you can take. Any other integral curve will be contained in that. So that's a maximal integral curve. Okay, so this is just a quick review of what we did last time. And as I said before, I mean, so far, we haven't seen nothing really good about manifolds. And now we are going to see it. Basically, all that we have been studying is how to obtain new manifolds. when we saw the differential was to use the inverse image to find submanifolds and so on. But now we have interesting things. So this is what we have so far. We have this. I have a vector field on a manifold. I take a base point, and I just found a curve, right, on the manifold, such that the derivative of the curve equals the vector field along that curve. And we only have some normalization condition. Okay, now the idea is not to obtain one internal curve, but to have a lot of them, a whole collection. And this is what we have and what we will see that flows. We would like to understand what is a flow. Okay, the whole concept of a flow, first let me give you what we are aiming at. So I have a vector field. Sorry, now I don't need this point. I have a vector field. Well, it is a reference point, so let me, yes. I'm going to take, or there's going to be a neighborhood of that point, and we are going to obtain some family of diffeomorphism. So from a vector field, we are going to obtain many diffeomorphisms that are related to the vector field. And this collection of diffeomorphisms is called the flow, or the flow of the vector field. Okay? So roughly speaking, this is what we're going to have. All of the orange lines corresponds to distinct internal curves. Of course, we have the one through P, but there are many others that do not belong to P. Okay? Now, before moving on, I would like you to think about this. So you have a vector field X here. And I draw P and the internal curve through P. There it is. Now take any other point that does not belong to that internal curve. This point. Again, we use the previous result. I have an internal curve here. Now, my question for you is, can these two intersect? This internal curve with this one?
Not.
Why not?
It will violate the uniqueness of the solution of a differential equation.
How come?
If I recall correctly, if we have a rectangle, the two solutions to this differential equation cannot intersect. So otherwise, it would mean that it won't be unique. So
Okay, so there's some uniqueness, but also like just like the picture. So I have here one curve for a point P. I take a point Q, not on the internal curve. And I have this. What is happening there? So first of all, because they are integral curves, at this point, the vector field should be something like this. And at this point, the vector field should look something like this. But that's not a vector field, because at one point I have two arrows or two vectors. So something like this cannot happen, right? Now, let's go to Moises' comment. So something like this cannot happen. But what about something like this? Because here they touch, and I don't have the problem that I had before, right? I have the same vector, only one vector at a point. And that's where the most advanced argument that Moises mentioned applies here. The uniqueness of the solution. Okay? So here, first, you can just rule it out because you will have two distinct vectors at one point. And that's not allowed by a vector field. So the only thing that it might happen is the second drawing here. In that case, both curves intersect at one point and they agree on the vector field. So here, on the second case, my argument that I use here doesn't work. And that's where Moises' argument works. So the integral curves cannot intersect each other, okay? Also, we discussed this last time. Remember that a point can also be an integral curve. Remember when that happens?
I didn't catch that. Can you repeat it?
So a point can also be an integral curve. What I'm saying, a constant curve, a constant function, see, this can be constant. Why is that? Why can that can really happen? A point can be an integral curve. What can you say about the vector field?
It is the zero vector field. Is it?
Pardon?
It is the zero vector field?
Right, so at that point, the vector field vanishes. It is a singularity or a zero of the vector field. So you can have exactly something like this, right? Maybe there's some point there or here. In that case, for any p, you always lie on that point. And that means, and it is equivalent that the vector field vanishes at that point Q. Okay, so again, now the whole idea about a flow is we have a vector field and we're going to put all together all of the integral curves. And that's going to create me some functions, diffeomorphisms, and they are called flows. And that's something that you might be familiar with. Let's see if this works. So you have some vector field there, and you see how it was moving before. Now let's see if we have some other vector field here. There's a vector field, and then you have the flow lines. They are also called flow lines. Okay, so this is what we would like to have now. And it is just the collection of all of the integral curves. So that's the vector field. That's another vector field, and well, this is something different. This is just a family of vector fields. Only at the beginning there were some flows. And then next, the flow. You see how it's moving? So this is what we would like to formalize. And have you seen this type of things before, the flows?
Yes, in the math models class, we've been using flows or vector fields to give qualitative approximations of how the system behaves.
Right. So okay. So that's good. So I just wrote the corresponding result. In Euclidean space, I'm not using manifolds. So this is it. Even because they are in Euclidean space, they use this notation. So this is our vector field. I have some open set V. I have the vector field F. And then these are the conclusions. In some smaller subset of V, I'm going to define the flow. So this is epsilon is going to be the domain of my integral curve. So I mean, from that point on, it is very important. You should realize, okay, I have an integral curve. I have some epsilon 1. I take another curve. I have an epsilon 2, and so on. But on an open set, you have infinitely many epsilons. So you can always say, okay, I take the minimum in order to define all of the integral curves. But you cannot talk about the minimum because there are infinitely many integral curves. So you will talk about the infimum. But it so happens that it is positive. It is something that it is positive. So this is more or less of what this is saying, this epsilon. So that all of the integral curves will have a common domain minus epsilon comma epsilon. Right? So this is the integral curve. I put T here. At 0 is the identity. And this is the differential equation of the integral curve. You see Q is fixed. It's any point on W. And if I take the derivative with respect to T, I get the vector field at the point. Right? So this is just what we see as the flow of a vector field. The only input is this, and the output is this with all of this. Okay. So this is just some observations. So this is actually the integral curve of the vector field F at P. Right? So we will use this notation for this, okay? YTP is what is given on the theorem, and we will call it like this. Now, okay. So this is a collection of smooth functions. This is usually called the flow of the vector field. I just wanted to call flow. We will justify all of this. And notice that it is defined in principle on a smaller set of V. Now, let's see a couple of things about these functions. Remember that they are governed by this. That means they are governed by this theorem here. So let's take, I want to do this. So we have to be a little bit careful here. Like P and S have to be on the interval. P has to be in W. And also this one has to be in W in order to make all of this that makes sense. So I want to compare these two. So I think if we put aside all of those technical details, T and S in epsilon, T plus S in the interval of epsilon, and all of that, the whole idea, and I want you to pay attention, is to these two things that we can do, this and this. Okay? Now, so for the moment, let's think that S is fixed, also P, and we would like to think of them as functions on T. So T will move a little bit. So let's think about that function. And that function, it will happen to be an integral curve. And it is actually a shift of the integral curve, because it's not normalized at zero. At zero, I have P, but it's not zero, it is minus S. But other than that, I have this by the theorem. The derivative is equals to this. Right? So these two things are telling me that this function is an integral curve of the vector x or f. But the only restriction is that it is not normalized so that at zero equals p. We have to evaluate it at minus s to obtain p. So that's why we might shift it. And now this is that satisfies the normalization condition. At zero equals p, and the derivative is going to give me this. So this is actually the integral curve. Okay? Now again, also, we go back to the uniqueness. We obtain that there must be equal. Okay? By the uniqueness of the integral curves, I get exactly that they are unique, that they must agree. Right? If you look at this this is an internal curve, right? But when t equals 0, it's an internal curve here. Right? So these two internal curves agree on one point, and they are internal curves of the same vector field. So they must agree. And that means that we have this relation among the distinct functions. Okay, then, so this is something that it is very, very important. Did you also see this relation, Moises?
I don't think so.
Okay, okay. So because this is very crucial. I mean, basically, this condition is what allows you to see the movie actually flowing. So you take a point P, so this is what we had above. I have P, and this is the internal curve through P. So maybe here it is at point T. Maybe here it is at point S, at time S. And here at time, okay? So that curve is my internal curve of the vector field. So let's do it backwards if you want. And I'm going to use x. Remember that f is, okay, I will use the f as in the theorem. So this at 0 equals p. And when I take the derivative at time t, I get the vector field like this. Okay? That's what we know. But now, let's change p a little bit. Where a is some constant. Okay, what happens with the derivative of c with respect to t? So but this is just this derivative, right? But because I have just t plus a is the same as the derivative of t. But now at the point t plus a, where I evaluate. By definition, this is the vector field f but we know that this is the same as C of t. So, okay. So, this is the image of C of P. Here is P. What is the image of this curve? As I said, in M or in Rn, it is the same curve, right? But the only trouble is that at 0, or maybe now here, this is C of minus A, right? But I want you to understand that as I said, the image is the same curve. And what we know, because it is an integral curve, so the tangent vectors agree with the vector field at those points. Okay? So it's just we only changed the parameter t, we shifted the domain only. Okay, so this is crucial to understand this for this, because what you have here, what is it? At time 0, you are here at P. Let me make the drawing again. Okay, so Salvador just left. Let's wait a few minutes and see what happens. So, Moises, you were telling me that you didn't cover this part.
No, but I think it was well, it was assumed that
Right.
it was fairly obvious. But
Okay. Now Salvador is back. Okay, you're back. Right, so this is important because it's telling me, okay, you're just moving always on the same curve, the point. And if after time S you are here, well, there's no problem because you can start at time S and then move along. So I move t units and I'm here, which is the same that if my initial point, I move t plus s in time. Okay? Right. Nice. Now, an important observation of this, and that's the third part, is that we know that in quotes, they are diffeomorphisms. We know what is the inverse. Right? Now, this is the other subtlety that we need to address. Remember that phi t Okay, that's why so the theorem says you have an open set V, and then there exists an open set W about P. Okay, so when you flow, you might get out of W, but you always lie on V. So what I want to stress, we don't have the same domain and image. So to say that they are diffeomorphisms, but that will come later on, right? In order to have diffeomorphisms, maybe this must be the same, but that will be apparent later on. Basically, we would like to use this on the whole manifold or the entire space. Okay, so this is what we have so far. And now let's do an example. Again, I'm just doing this on Euclidean space at the moment. This is an example that we covered last class. We have this vector field on all of R2. And if you go and, we actually work out the integral curve of that point. We solved that problem. We had a system of ODEs. We solved it. It was true for all of T. And that was the integral curve through this point here. That the integral curve appears to be a circle, the unit circle centered at the origin. Okay, now, but when we solve that, this is the system that we were to solve. The initial conditions gave us exactly this, but the general solution was this one. Okay, now, so in this case, the flow looks like this. But this is good because you see now, I don't have to shrink to a smaller set W. It is on the same manifold that we have the vector field. So this happened, I have those functions are indeed defined on all of the open set. And they are truly diffeomorphisms. Right? The theory only tells us that on a smaller set you may define them, but here it happened that there's no restriction whatsoever. I can do it on the whole space of R2. Right? And again, I forgot to mention this. I didn't say it. The other observation of this is and it was given on the first part. Okay. The initial condition. So here the initial condition, now we can say that it is the identity on R2. Now, the important aspect is from one vector field, I have a whole collection of diffeomorphisms. right? And at least let's remain on R2 with this example. You see, if I tell you, okay, you have your manifold R2, and I need you to give me some diffeomorphism. It's complicated to come up with a diffeomorphism. However, if I tell you, give me a vector field on R2, that is much easier. I mean, you just have to plug in here some function, and you have a vector field on R2. So that's why this process from a vector field, obtaining a flow is important because it is more complicated to obtain diffeomorphisms, and it is easier to work with or define vector fields. And also, from one vector field, we get many diffeomorphisms. Okay, this is good. At this point, any questions? Okay, so let's move on. I have another example, again, only on R2. The example that we saw at the beginning of the class that we also covered last time. So I have this vector field, and I just wrote the flow. I didn't put anything whatsoever. Again, there's no need to shrink to a smaller set. This holds on all of R2. And also the parameter T, there's no restriction. You can do it on all of T. Is this good? Now, when we saw this example last class, I made a slight modification just to understand the domain of the integral curve. Let's do it here again. Remember that we remove a point. So let's do it again. I have this. I have the same vector field. And for instance, if P is the point 0, 1, we know what the integral curve looks like. So remind me, what is the integral curve of this? It is the same problem that we saw at the beginning of today's lecture.
T and 0.
Hold on. So again, what it says?
T and 0.
T, 0. But when t equals 0, what happens?
It's in the domain, so
No, if I put t equals 0, I don't get p, right? So here I must put a 1. Because at 0 I have, which is me. That's the initial condition that we require. And the other thing is, so this is the integral curve of that vector field. However, what is the domain of T? Oh, sorry. So here, so this word, this is R, right? So this example is not going to work. I wanted to have a distinct domain. What do I have to change? So let's change this. So this was my mistake. 1, 0. Okay. Sorry about that. What is the integral curve?
T plus 1, 0.
And now 0. Yeah, now it's 0. Yes. And now I have this at 0. And now what is the domain of this function?
The reals, but 0.
Okay. No, but
The reals, but the minus 1.
yeah, no, but we need, remember that the definition was an interval. You are giving me 2 intervals. So that's true. In order to see how this function maps to my manifold, what you say is correct. I agree. But in order to be an integral curve, I need an interval. And I must choose the one that contains my base point. So what is the domain here?
From -1 to infinity.
Like this, right? Okay. So let's see here on the picture. So that's my point in gray. This does not belong. So all of this is my integral curve. What you said is correct. In order to be a function from some domain to the manifold, but for the purpose even of the flow, and that's what we will make precise, your answer is not the right one. Okay? So for instance, because under the flow, this point is going to be moving along here. Okay? It will move here a point under the flow. Now, so you see, as opposed to this example, if I would like to write the flow, I have to be careful. I can no longer say this. And you can look at this either way, only on points on the x-axis. If I'm there, I can move forward in time with no problem. However, if I'm here, I can move forward, but only before I reach the origin. I cannot move forward anymore. So the point doesn't jump. That's why what you said in terms of the flow is not correct. So the point cannot jump. Or if you would like to think about it on the other direction, sine minus t, let's go backwards in time. If I have this point, I can move back only up to this point. If I'm here, I don't have any limitation. I can move backwards in time all the way up to here. There's no restriction. So this example makes sense to all of you? Now, if you would like to write down the flow, is where, let me go back to the theorem. The W is important. And whatever you choose for W will affect this. So let me do the drawing again. So we don't have this. Okay, you have this. Oh, sorry, this is, let me put it here where the example starts, sorry. So I don't have this. So we would like to talk about the flow now, about a point. If your point is here, you can take W to be the upper half plane, and the flow will be defined on all of the reals with no problem. That will work. So for this point, you can take W to be all of the upper hemisphere, and the minus epsilon epsilon will be the reals. Okay? However, and that happens also if you take a point below. That will be no trouble. What you have to be careful is when P lies in the x-axis. Here. Okay? Now, the open set W that you will take, what could it be? It would be this. But now your parameter will be exactly minus 1 comma infinity. Well, I haven't said what P is. Let's say that P is exactly what we have here. So that will be W, only half of the space. And for all okay? Even though up here you have no trouble, you can move around whatever you like, but it is a time that has to work for any point in W. So meaning this, what's a limitation? Remember the theorem. So this is a uniform map for any point in W. Okay? So this is an example where we don't have the global, the entire space. Of course, W can be also a smaller one. I'm just taking the maximum that you can take with the geometric limitations or abstractions that you have. Good. Any questions? So these are flows on Rn. Eventually, we will study this on manifolds. Okay. But I mean, the idea is exactly the same. So here, what I'm very, very important, you need to understand this. If you understand this, forget about Rn. If you understand this in R2, then you have it. Okay. Going back to this example, we saw the integral curves. Remember also that here we have an integral curve, which is a point. The vector field vanishes there. Here, the integral curve, parallel lines, parallel to the x-axis. Okay. Right. So far, any questions or comments? Nice. So this is just what we have done. This is like the whole idea. You have a vector field, and then you look at smaller neighborhood, and you will get the flow there. Okay. Again, they are not diffeomorphisms because, strictly speaking, because we have different domains, but eventually they will become diffeomorphisms of the manifold. Okay. Right, so here is, we would like to think this as diffeomorphisms of the manifold. Right, now I put here the U, the open set in Rn, and that's why I didn't put diffeomorphism of what. But I want to here is just like the set of ideas. But this is actually what it is happening. with the example of the rotations in R2 or the flow in R2, we actually got diffeomorphisms and everything working out. Let me tell you what we are doing in this context. Okay? Now, this is very interesting. Look. What is this? Remember, this is my notation of what? Come on, I have been using this from the beginning. Vector fields. This is the set of vector fields. Okay? Now, let's stick with vector fields in R2. What can you do with vector fields? You can multiply them by a scalar function, or even a scalar. And also you can have two vector fields, add them up, and you have a new vector field, right? So this set of vector fields in R2 is a vector space, right? It is infinite dimensional, but it is a vector space. Usually we write it like this. Some function here, some function here. And I'm going to say that they are only on R2. So it is clear that the set of vector fields is a vector space. Nice. Okay. Now, what about diffeomorphisms of R2? What is the algebraic structure of the diffeomorphisms? A long time ago in the homework, you saw that the composition, it is also a diffeomorphism. A diffeomorphism also is something is a diffeomorphism means that the inverse is also a diffeomorphism. So what is the algebraic structure of that?
Sounds like a group.
It's a group, right? What is the identity element of that group? What is the identity element on the diffeomorphisms?
The identity,
Moises? I mean, it is a group under composition of functions, right? So the identity element, what is it?
Sounds like the identity mapping.
The identity map. Okay, this is the identity element of the group, the identity function. Okay? Good. So let me tell you what is the flow that we have seen, what is actually what you are doing. You are doing something very interesting, which is nothing new in terms of the concept, but it is something very, very sophisticated, what you are doing here. Remember the following problem that we discussed a few weeks ago. Imagine in R2, if you have a vector at one point. I have a vector in R2 at some point. Let's say at the origin. Do you remember that you were able to construct a curve such that it goes through that point and the derivative of the curve agrees with that vector? Remember that we have seen this? It was a problem that I asked you to tell me how to solve it, and both of you told me how to solve this problem. Okay? So if I have a vector, only one vector, I'm not talking about vector fields. If I have one vector in R2, you are able to tell me how to construct a curve that goes through that point, and the derivative is that point. Most of you agree on this? Okay. So this is something, I don't know, maybe you don't need to take this class. Maybe in high school, if just on R2, if I give you the vector, and okay, draw a curve that will give you, the tangent vector will be the given vector. I'm sure that you will be able to solve it. And that's the tangent vector at that point. Okay? Now, let's go to the concept of a vector field. What we have seen today. Again, let's stick with R2. I give you a vector field and we found the flow, like for the rotations or the translations. That what you understand very well is the same as this, but in infinite dimensions. So using the flow, you just solve this problem, but in infinite dimensions. Because this is an infinite dimensional vector space, and we took here one element, one vector field, like DDX only, or the one given by rotations, one element, one vector field. Using the flow, you constructed this. what you constructed on the group of diffeomorphisms was a curve. This is a curve of diffeomorphisms. This is the identity element, Phi T1, I don't know. So you constructed a family of diffeomorphisms. And exactly what it means is in this infinite dimensional group, diffeomorphisms, you found a path, only a path of diffeomorphisms. And basically what you were doing is you found a path such that at the identity, the derivative is the given vector field. That's exactly what you were doing. That's why the result only cares about some epsilons. But somehow we managed to extend the curve in some cases. But this very naive thing in R2, I give you a vector in R2 and you find a curve, is exactly what you're doing with flows. But in some very sophisticated vector field and in some very sophisticated manifold, which is the diffeomorphisms. Okay, so that the flow is a family of diffeomorphisms. So it's a path such that the derivative at the identity element happens to be the vector field. That's what you were doing here with the flows. Okay, moving on. Questions?
Yes, you say something along the lines of solving it for infinite dimensions. What do you mean by that?
Right, I mean, so first, this is the problem in R2, right? You have the vector 3, 4 at the origin, and you would like to have a curve that goes through the origin, and the derivative only at the origin is that. What is that curve? So, yeah,
wherever curve that satisfies that condition. For
there are
example,
many. So give me an example of one. You want at 0 to be the origin. You want this, right?
yes, let's say the line t minus 3 and t minus 4.
But hold on, but what about this? This is the derivative.
No. T minus 3 and t minus.
Yeah, but the derivative is going to give you 1, 1. Your example, Moises, it satisfies the first condition at 0 equals 0, but the derivative will give you 1, 1. And we need the derivative to be 3, 4. Okay. So this is one example, right? Is this correct for everyone? Okay, so that is a curve in R2 at 0 equals 0, and the derivative is 3,4. Okay. Now notice, this is different than the integral curve, because the integral curve, we care about all the points of the curve. Here, I only care about one point. So you can come up with many solutions. This is one of them. Nice. So you solve this. So this makes sense, Moises?
Yes.
Okay. So this was the problem on R2. Now, same problem, but now here. Because it is a group, there's a distinguished element, which is the identity diffeomorphism. Okay? That's why I don't take any other diffeomorphism. I take the identity element. And now, in quotes, you take a vector here. And by a vector, I mean a vector field. And the flow, what is the flow is something like this. It's a collection of Vt like this, because phi of 0 is the identity, that's the initial condition. And that path of diffeomorphism, phi of t, being the flow of x, means exactly that. That the derivative of 0 is this vector. And I'm saying infinite dimension because this is not a finite dimensional manifold, it is an infinite dimensional manifold. Maybe that's not easy to understand, but this vector space, maybe that's much easier for you to picture. It is an infinite dimensional vector space. So that's why I said that this is the infinite dimensional version of this problem. Finding the flow is the infinite dimensional version of this elementary problem. So this result, more or less, is saying that. This parameter will give me a path of diffeomorphisms. And I mean, also, at least that idea that I explained, that's why here you have this, because you only care about the derivative at one point. So that's why you only define the curve in a small neighborhood of that point. You don't see the rest, and you don't care. So that's why this result, the conclusion, is only in a small neighborhood of 0, meaning in a small neighborhood of the identity diffeomorphism. In order to solve the problem in R2, I only care about the curve in a small neighborhood. I don't care about the rest. The same here, only in a small neighborhood of that diffeomorphism. And that's where the minus epsilon epsilon of the theorem comes in. Good? Great. Any more questions?
So in some sense, the flow is like a gathering of a bunch of groups of integral groups.
Right, right. Each flow, so each flow is a whole collection, right? Let's take this example. So, right. This is the flow. And you remember what was the integral curve, right? If I take P, I mean, now you are like experts on this particular example, which is enough. Let's take P to be an abstract point. What is the integral curve for this flow?
And that should be T plus P1, comma, P2.
Like this, right? That's the general format of an integral curve. So the flow, you fix a T, and then you put all together all the flow lines. So the flow exactly is like gathering all the flow lines at a point T. Okay. And that was also what I was trying to say on this picture, right? So you have the integral curves, the flow is you take all of them. Now, it is oh well no, I think I wrote it down here somewhere. Yeah, here you see. This is where I put it now explicit, and this is concrete mathematics. So remember that the YT is the integral curve. And then that's what the flow is, the collection of all the integral curves. Okay. Jesus, that makes sense?
Yeah, that's fine. Thank you.
Okay, now, again, just understanding this makes sense to understand it on a manifold. This means the intuition that you can obtain from these examples, that's a very good starting point. It's nothing different when we go to manifolds, okay? So if I would like to define the flow on a manifold, so I have my manifold M, I have a vector field there. And remember that we use some base point. So I take a point P on my manifold, and I would like to obtain the flow. Usually this is called the local flow. So I take a neighborhood chart about P. And then what happens? So if I make a chart about P, now I am in Rn here. And I know how to come up with a flow in Rn. But in order to have a flow in Rn, I need to have a vector field. So what we must do is to take this vector field and somehow define a vector field here in Rn. And then use what we know about Rn. On Rn, if I have a vector field, I can talk about the flow or local flow more correctly. And then using the same chart, you come down to the manifold. Okay? So in order to have this, there's a vector field here and get a vector field here, we need to define the push forward. Okay? Now, remember that we have seen that when this is a chart, this is a smooth map. So we will use that fact that the chart is a smooth map, is even a diffeomorphism with some open set in Rn and an open set on M. Okay, so let's move. Let's see the push forward now. So given a diffeomorphism, this is important. I'm not taking any smooth function. It has to be a diffeomorphism. And if I have a vector field on M, I'm going to obtain a vector field on N, and that vector field is called the push forward. And it uses this notation that we have used before. And this is the definition of the push forward. So this is a vector field on M. So if I have a function and I have a vector field, how do I define this? So I just compose, because I have a vector field here, which is X. Okay? Good. Now, well, point-wise, I have it here point-wise. This is what it is. Now, I mean, we have seen this in the derivative. I mean, it is precisely the derivative that we have seen before. However, before we only saw it, I take a vector on the tangent space and I define f or phi lower star or that vector. That we have seen before. Now, the only distinction, now we are doing it all together. There's nothing wrong about that, but you have to be careful because, so I have here P, and I'm defining a vector here using this formula, right? Okay. Now, why is it important that it is a diffeel? You see, imagine that you have here a different point Q that also maps here. Then on one side, you have the arrow that I wrote that comes from this. But if you let the derivative at Q and move this vector, you might get something different. And so here, you don't have a vector field because on one point, you might have two vectors. That's the only thing that you have to worry about. Other than that, it is the standard derivative that we have seen. Okay, so this we have seen before. It is the same. There's no difference. The only thing that we require, because I want this to be a vector field, not only a vector on the tangent space, but I want that to be a vector field on N. So first of all, on any point on N, I need to have a vector. So that's why phi has to be surjective. Also, since I want it to be a vector field, on any point, I can only have one vector. I cannot have more than one vector. And that's why phi has to be 1 to 1. So vector fields can be pushed forward to vector fields using diffeomorphisms only. A vector, you can always push it forward to another vector. And we use the same notation. Okay, so this is the push forward. And the whole idea is that I'm defining a vector field on M. That's why I need phi to be a diffeomorphism. Okay? But it is the same phi lower star that we have seen before. Like if you put coordinates, it is the Jacobian matrix. It's exactly that. Okay, now that's how we are going to define a flow on a manifold. I have a vector field on M. I pick a chart. I have a vector field on U. Using the chart map, I'm going to push forward that vector to have a vector field here. On Rn, I define the flow and I move back to M using this. The same idea that we have used before. We always go to Rn or Euclidean space to do what we know how to do and then come back to the manifold. Great. So time's up. We will leave it here. And what is very important is to understand the concept of flow. And remember that we will have 3 guest lectures. One of the lectures, it is important that you know how to come up with the flow of a vector field. So you really need to understand this.
Who are the guests?
You're not paying attention, man. So
They're the ones in the page, right?
yeah,
Page.
so we will have 3 guests. One of them is Lauren, the author of the book that we are following. And then we will have Fabian. Fabian is the one who will talk about vector fields and flows. And also Efrain. Now, I mean, a dynamical system is precisely a flow, not the whole concept. A dynamical system. Phi of 0 is the identity, so nothing moves. It's like the initial point, and then as you let t move along, everything progresses. So the flow is the dynamical system. And sometimes you can go backwards in time, so you go minus t. So the flow with those characteristics is the dynamical system that you've seen. That's the picture in the videos. As time progresses, what is going on? So it is important from that reason, and it's not only important on Euclidean space, it is important on manifolds. And that's what I'm saying, like this is like the first thing that we are actually seeing that is not related to manifolds or to come up with new manifolds. So it is just to have the flow. I mean, here, this is not a class of dynamical systems, but what you care about the flow is what are the stationary points, meaning the points that don't move along the time, or the zeros of the vector field if you have it. What do you care also about dynamical system? You take a point and you have the integral curve. So what you care in a dynamical system is if you will come back, if it is periodic, if you have periodic orbits. That is, if some points, the integral curves are circles. You eventually come, not on every point, but that you will have at least some points when you are just periodic. So that is type of the behavior that people in dynamical system are interested in. Just the beginning. I mean, there is more than that. But this is just like the basic, the first steps in having the flow, trying to understand the behavior of that. Right. Any more questions? Okay, then, so if not, we are done for today. And I will see you next week. Okay?
All right.
Yes. ¿Tienes tiempo?